Welcome back. In this fourth lecture, we will cover manometry and surface tension. Manometry is connected with measuring the pressures. One of the simplest manometer is a U2 manometer. In this case, in the picture shown, we have a bulb A which contains a gas and then a liquid column shown in red in a tube. The difference in the level in the two limbs is H. The pressure at A can be measured by using the principle that the fluids have the same pressure at same horizontal level if the fluids are connected. So in this case, point 1 and point 2 will have the same pressure. Since the density of the gas is very small, we can say PA is like P3 and P3 is P1 minus rho GH, because from P1 we are going up a distance H. So it is minus rho GH and P1 is equal to P2 is equal to atmosphere. Putting it all together, PA is equal to P atmosphere minus rho GH. The pressure of the gas inside the bulb is lower than the atmospheric pressure by an amount rho GH, where rho is the density of the manometric fluid in the tubes. Consider two bulbs A and B. The bulbs A and B are filled with a liquid of density rho 2. These bulbs are connected with an inverted U tube. The black fluid has a density rho 1. The difference in the level of the fluids is H as shown. Clearly, we can calculate the pressure difference PA minus PB through a process similar to what we did last time. We seek points on the horizontal level connected by the same fluid. Points 1 and 2 are 2 points at the same level connected by the same fluid. So the pressure at 1 must be equal to pressure at 2. We'll exploit this fact to calculate the pressure difference PA minus PB. We go up or down from points 1 and 2 till the next interface. In this case, PA is clearly P1 plus rho 2 GH1, since the uncolored portion of the tube is filled with a fluid of density rho 2. So pressure at 1 is higher than pressure at 1 by a liquid column of height h and of density rho 2. Similarly, P3, which is below P2, is equal to P2 plus rho 1 plus GH, where h is the height of column 3 to 2 and rho 1 is the density of the fluid there. Similarly, PB is equal to P3 minus rho 2 GH, since B is higher than 0.3, so the pressure is lower. Putting it all together, that is summing these three equations, we get PA minus PB is equal to rho 2 G H1 minus H minus rho 1 GH. If we know the heights H and H1 and the densities rho 1 and rho 2, we can calculate the pressure difference PA and PB. We do another example, a little more complicated manometer. Here we have a bulb with a pressure P of a gas, and the manometer is three fluids of density rho 1, rho 2 and rho 3 as shown. We use the standard method of calculation that we seek points at the same level connected by the same fluid and equate the pressures in two different limbs, and then we move up and down within a fluid to the next interface. Let's mark the points 1, 2, 3, 4. These are the levels at which the fluid changes. Clearly, P2, the pressure at point 2 is greater than pressure at point 1 in the rightmost limb, and is given by P2 is equal to P1 plus rho 1 G H1. In the second limb from the right, the pressure at the level 2 is the same as P2. And so pressure in this middle limb at a level of 0.3 would be same as pressure at 3. And the pressure at 3 is lower than pressure at 2 by amount minus rho 2 GH2. So P3 can be written as P2 minus rho 2 GH2. Now 0.3 is above 0.4. So pressure at 0.4 is P3 plus rho 3 GH3. Putting it all together, we get P4 is equal to P1 plus rho 1 GH1 plus rho 2 GH2 plus rho 3 GH3. Since P1 is the atmospheric pressure, so the gauge pressure at 0.4, P4 gauge, is given simply by rho 1 GH1 minus rho 2 GH2 plus rho 3 GH3. In all these applications, typically we'll have to make two measurements of levels, and then the pressure related to difference between two levels. Sometimes we use with a much larger cross-section area, and the resulting reservoir manometer is as shown. There's a fluid in a very large cross-sectional area reservoir to which a pressure P is applied. Because of this pressure P, the fluid contained within the reservoir rises up a thin capillary. Since the diameter of the capillary is very small, as the fluid level changes in the tube, the level within the reservoir does not vary significantly. And we can assume this is at a constant level. So that by just measuring the height of the column on the scale provided, we can find out the pressure P. This is used in a conventional blood pressure measuring equipment. Here at the bottom, there's a large reservoir, a relatively large reservoir of mercury, which is connected to a very fine bored tube against a scale. It is kept vertical, and when the pressure is applied to the reservoir, mercury rises as a column within the capillary. And by reading the height of the mercury column on the scale, fixed scale provided, we can calculate the pressure head. This is a reservoir manometer with berry tubes, a multi-tube manometer. Here it is being used to measure the pressure distribution about an aerofoil. The sketch shows an aerofoil with a large number of holes. From each hole, a tube runs to one of these tubes, many tubes. There is a reservoir too, which contains the fluid. And so the height of these columns give an indication of the relative levels of pressure at the different holes in the aerofoil. This is another device, an inclined tube manometer. See the pressure difference that we measure is rho GH. If H is small, it can lead to error. So, to increase the value of H, we incline the limb of the manometer at an angle theta. The pressure at this point, which should be equal to the pressure at this point, is higher than the pressure at this point by the amount rho GH. But H is L sine theta. So the pressure P is rho GL sine theta. This is a commercially available inclined tube manometer in which the two pressures are connected at this nozzle and in this nozzle, and it measures the difference along the scale shown. This another inclined tube manometer in which the inclination is variable. The errors in very low measurement of mercury, very low measurement of liquid heights is very large compared to errors in the larger height. So we need more inclination when the height of the column is less, but we can do with lesser inclination when the height of column is more. So in this commercially available variable inclination manometer, the tube is curved in such a manner that the inclination at low values of head difference are large, but the inclination at higher values is low. In fact, the tube becomes vertical towards the higher end. Bourdon gauge is a gauge that is used to measure the pressure most commonly. It uses the property that if a curved tube of an oval section is pressurized, it tends to acquire a circular section and in the process it straightens out. This we show here. We have shown a curved tube with an oval section shown here. As we apply a pressure P at this end, the cross section of the tube tends to round out as shown here, and as the section of the tube changes, the curvature of the tube decreases, its radius increases, so it expands out. And it expands out, the pointer attached at the end moves on a scale, and this gives a reading of the pressure. This is the basic principle of a Bourdon gauge, one of the most commonly used pressure measuring equipment. The other types of gauges use bellows and capsules. In this first picture, there is one pressure which is applied on the outside of the bellows, The other pressure that we want to measure is transmitted inside the bellows, and depending upon the pressure, the bellows move in and out. And as the bellows move, they push the pointer around a scale. More the pressure, more is the reading on the scale. Similarly, we have a metal capsule here, or a diaphragm in the form of a capsule. There is a case pressure, the atmospheric pressure in most cases, which is applied here, and then the pressure that we want to measure is applied there. Because of this difference in pressure, the capsule inflates or deflates, resulting in a motion that is converted into the motion of a pointer on a scale.
Tire gauge, based on the Borden tube principle, reads the tire pressure as a gauge pressure, about 34 pounds per square inch, psi, or 234 kilopascals. Gauge pressure is the increment of pressure above atmospheric pressure. This is another instrument based on the same principle, but designed to read absolute pressure. It reads about 14.4 psi when open to the atmosphere at the altitude where these experiments were done. If we apply pressure above 1 atmosphere, the reading increases above 14.4 psi. As a vacuum pump draws the pressure down, the reading tends towards 0 on this absolute pressure scale. Both these instruments operate on the Borden tube principle. The curved tube is connected to the high pressure being read. A higher pressure tends to straighten out the tube and vice versa. The end of the tube is connected to a linkage that drives an indicating needle on the face of the pressure gauge. There are other instruments to measure pressure, such as this diaphragm-type transducer. A pressure difference across the thin metal diaphragm causes it to flex and changes the internal capacitance of the transducer, which is sensed electrically and converted to a pressure reading. This is a modern piezoelectric pressure transducer. Its tip contains a crystal that responds to pressure changes by generating an electric charge. The amount of charge can be converted to a pressure reading through calibration.
Another common type of pressure pickup is a capacitance type pressure pickup. In this case, we utilize the fact that as the distance between two charged surfaces changes, the capacitance changes. And so that results in an electrical signal that measures the difference in pressure that is applied here and the pressure that is applied on this side. On one side is the atmospheric pressure usually, on the other side is the pressure that needs to be measured.